To everyone. I am Dr. K. Suresh, Associate Professor, Department of Mathematics, St. Joseph College of Engineering, Chennai. Today we are going to discuss about the topic contour integration. So, using contour, you can evaluate the integration. So, it has three types. The first types becomes the integration of the form 0 to 2 pi f of sine theta cos theta d theta. It's the first type of contour integration. Next, the second type becomes integral minus infinity to plus infinity, numerator p of x divided by q of x dx. This type of integration we can evaluate by using contour integration. Here, the numerator p of x and the denominator q of x is nothing but polynomials. The denominator q of x at least 2 degree greater than the numerator p of x. So this type of integration we can evaluate by using concept of contour integration. And the third type of contour integration, integral f of x sine mx dx or integral f of x cos mx cos x cos nx or mx dx. So third type of contour integration. So now we are going to see about second type of contour integration by using an example. Considering an example in the next slide. Now consider the problem. Evaluate the integration integral minus infinity to plus infinity x square minus x plus 2 divided by x power 4 plus 10x square plus 9 into dx using contour integration. Using contour integration. Now, how to use contour integration here to evaluate the integration? So, solution. Consider the function f of z. Consider or let f of z as the given integrand function in terms of z, that is z square minus z plus 2 divided by z power 4 plus 10 z square plus 9. Consider this as f of z. Now, we have to consider the integration. Also consider integral over c f of z dz as integral over c z square minus z plus 2 divided by z power 4 plus 10 z square plus 9. Consider this integration. So here, what is c here? Where c is . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . the contour. Here we are using contour integration, so we are going to use the contour. The C is the contour consists of, C is the contour consists of upper of circle, upper of circle, upper of circle, modulus of Z equal to R. We denote it as gamma. Gamma is the circle, mod Z equal to R, upper of circle mod Z equal to R, and the real axis from the radius minus R to plus R, minus R to plus R, which is our contour. For example, I can draw the contour here. Now this is our minus R and here is our plus R. So from the real axis, this is real axis x axis, and this is our y axis. Now this is our upper of circle. This is our upper of circle, which is modulus of Z gamma, that is modulus of Z equal to R. This is our, so this part I can differentiate by using another color. Now, consider the minus R to plus R and the upper of circle and this upper of circle this upper of circle. This is our contour. This is a closed curve. It's our contour. This is our required contour. Okay. Now the integral over C f of z dz becomes, so our integral f of z dz becomes along the C. What is C here? C consists of two parts. One is from minus R to plus R. From real axis minus R to plus R. The function now is f of x dx, because this is a real axis, f of x dx, plus and the circular part, that is upper of circle, gamma, that is the curve. Here f of z dz. So our integration interval C f of z dz becomes addition of two parts, that is minus R integral minus R to plus R plus integral gamma. Okay. Now we are going to evaluate the integral left hand side, that is integral C f of z dz. Now how to evaluate this? So to evaluate the integral C f of z dz, we need to use the Cauchy residue theorem. To use Cauchy residue theorem, we have to apply by Cauchy residue theorem by using Cauchy's residue theorem. By using Cauchy residue theorem, the left hand side interval C f of z dz becomes 2 pi I into sum of the residues of f of z which lies, the poles which lies inside C. That means sum of residues of f of z at the poles which lies inside C, which are all lies inside, which lies inside the contour C. This is a formula by Cauchy residue theorem. Okay. Now the right hand side becomes integral minus R to plus R f of x dx plus integral over gamma f of z dz. Now consider this as equation number 1. This is our first equation. Consider it as 1. So we are going to find the value of the integration right reference side. Okay. Now to find the value of the integration means we need to find the residues and the poles, and we have to find the residues, those poles which are lies inside C. Okay. First we have to find the poles of the given function. What is the function here? So f of z is f of z equal, here f of z equal to like z square minus z square minus z plus 2 divided by z power 4 plus 10 z square plus 9. This is our function. And now we have to find the poles of this function and find the residues at those poles which are lies inside C. Okay, first to find the poles of f of z. The poles of f of z are given by poles of f of z are given by the poles of f of z are given by 1 second. Poles of f of z are given by treating denominator as 0. That means what's the denominator here? Z power 4 plus 10 z square plus 9 equal to 0, which gives the poles of the function. Denominator equal to 0, which gives the poles of the function. Now consider this as put m equal to z square. Now letting m equal to z square means this becomes a quadratic form. That is m square plus 10m plus 9 equal to 0. Now this is a quadratic form. We can solve by factorization. We can write it as 1 minus 9. That means m plus 1 into m plus 9 equal to 0. Now we can use the value substitute the value. M as z square, that is m square z square plus 1 into z square plus 9. Now the values of z, that is poles of f of z are, this implies z square plus 1 equal to 0 or z square plus 9 equal to 0. So z square equal to minus 1. So that means z equal to plus or minus I. Next here z square equal to minus 9. Taking square root on both sides, they get z equal to plus or minus 3i. Now the poles of f of z are the poles of f of z are z equal to I, comma minus I, comma 3i, comma minus 3. So we get 4 poles of the given function. Here the poles which are lie inside are, okay, by using the contour we can find what is the contour here. Here our contour is the upper half of the semicircle with the minus r to plus r. This is our contour. Okay, so r is a very big value. Okay, modulus of z equal to r. So the positive poles which are, that is z equal to here, z equal to I, comma 3i. These are all positive values. That means modulus of Z to R are simple fold which are lie inside C, are poles, simple poles lies inside C, inside the contour C, because we are choosing the contour like this. And the negative poles, that is minus I comma minus 3i are that's also simple poles, but it lies outside C. Simple poles lies outside the contour. Lie outside the contour. Okay. Now, because the positive values are all on the upper part of the contour, that is the I, 2i, 3i, 4i, etc., etc. Then whether the negative part lie outside the circle, because this is this is minus I, minus 2i, minus 3. So we are going to find the residues of the poles which are all lies inside C. So here I and 3i are the poles which lies inside C. Therefore, we are going to find out the residues at the poles Z equal to I and the residues at the poles Z equal to 3i. Okay. Now to find residue of f of Z. So a residue of f of Z at Z equal to A. What's the formula for residue? Okay, formula for residue of a function with at the simple pole Z equal to A. Okay, now Z equal to A is a simple pole. Okay, now what's the formula? Limit Z tends to A, Z minus A into f of Z. This is the formula for finding residue at the simple pole A, small a. Here we are going to find out the residue of f of Z, at the simple pole Z equal to I. The first simple pole Z equal to I. Now by using the formula, what do you get? Limit Z tends to I. Formula is Z minus I into f of Z. Z minus I into f of Z. Okay, we can rewrite the function f of Z as where here f of Z is nothing but Z square minus Z plus 2 divided by Z power 4 plus 10 Z square plus 9. Now, this is a function. By using factor form, the denominator can be expressed in the factor form like this. That is Z square minus Z plus 2 divided by. Write it in the factor form. We can write it as Z minus I into Z minus I into Z plus I. Because I and minus I are the poles here. And the same sense is 3i and minus 3i are the poles. So we can write it as Z minus 3i into Z plus 3a. So this is our function in the denominator as a factor form. Now we can write this as limit Z tends to I, Z minus I. What is the function f of Z here? Here f of Z can be written as Z square minus Z plus 2 divided by Z minus I into Z plus I into Z minus 3i into Z plus 3i. Now cancelling Z minus I and Z minus I, we get, what do you get? Replace Z by I means this I square minus I plus 2 divided by I plus I is 2i, and here I minus 2i becomes minus 2i minus 2i and I plus 3i becomes 4i. Now what do you get? I square value minus 1. Therefore, the numerator becomes minus 1 minus I plus 2. This is the numerator. Whereas the denominator becomes 16 into I square value minus 1 minus into minus plus. Therefore, 16i. So, get that is 1 minus I divided by 16i. 1 minus I divided by 16i. This is our residue for the pole z equal to I. 1 minus I divided by 16i. In the same sense, we are going to find out the residue for the pole z equal to 3i. So residue of f of z at the pole z equal to 3i. This is another pole which lies inside C. So limit z tends to 3i. Formula is z minus 3i into f of z, which is limit z tends to 3i, z minus 3i into the function f of z can be written as z square minus z plus 2 divided by z minus I into z plus I into z minus 3i z plus 3. So while cancelling z minus 3i and z minus 3i, what we get? That means which is equal to replace z by 3i, we get z square means minus 9. Numerator z square means minus 3i the whole square, that becomes I square value minus 9 minus 3i plus 2 divided by, and while you replacing z as 3i, it becomes 2i into 4i into 3i plus I, 4i into 6i. 3i plus 3i, 6i. Replace z by 3i. Now, the numerator becomes minus 7 minus 7 minus 3i. Minus 7 minus 3i. Minus 7 minus 3i. Okay. Minus 7 minus 3i divided by, here 48i. 48 into I square value minus 1, therefore minus 48i, which is nothing but 7 plus 3i, 3i divided by 48i, 48i. Now we are getting two residues. Okay, two residues. Now from equation number 1, we have to, the value of the integration becomes 2 pi a into sum of the residues. So the next slide, using equation number 1, equation 1 becomes equation 1 becomes 2 pi I into sum of the residues. Okay, sum of the residues. What is sum of the residues? Sum of residues. Remove the residues at poles which lies inside C. In the right hand side becomes minus R2 plus R f of S dx plus integral gamma f of S dx. Okay. Now 2 pi I into sum of the residues. What are the sum of residues here? 1 minus I divided by 69 plus 7 plus 3I divided by 7 plus 3I divided by 48I. Addition of these two. Okay, which is our integral minus R2 plus R of x dx plus integral gamma f of s dx. Now this becomes the value of this is equal to 48I is our LCM. Now 3 minus 3I plus 7 plus 3I. Now the value is 2 pi I into, okay, well, cancelling 3. What do you get? Which is equal to 3I minus 3I get cancelled. So 10 divided by 48I. 10 divided by 48. Okay. Or you can write it as 5 divided by 24. 5 divided by 24. So here into 5 divided by 24. Now this becomes integral minus R2 plus R of x dx plus integral gamma f of z dx. Now while cancelling I in the numerator denominator, we get cancelling I 5 pi by 12 is equal to integral minus R2 plus R f of x dx plus integral over gamma f of z dx. So we are getting a result 5 pi by 12 equal to sum of two integration. Here, if the radius r tends to infinity, then integral over gamma f of z dz tends to 0 and z tends to x. When applying r tends to infinity, we get like this. So for 5 pi by 12, which is equal to integral minus infinity to plus infinity f of x dx plus 0, because integral gamma becomes 0. By using the formula, we get like this. Now, this implies integral minus infinity to plus infinity f of x. What is f of x here? Instead of f of z, we have to use, that is replace z by x. That means x square minus x plus 2 divided by z power 4. Sorry, that is x power 4 plus 10x square plus 9 into dx equal to 5 pi by 12. Which is the answer for the required problem. That is 5 pi by 12 is the answer. Now, we get the solution. So by using the contour, we reach the solution. The next, we are going to discuss about type 3 contour integration of type 3. So consider the second problem. This problem is a contour integration of type 3. So consider an example. There is a problem. Evaluate evaluate integral 0 to infinity cos ax divided by x square plus 1 into dx. So this integration is of the form integral f of x into cos ax, or in sin ax also you can use the same type, that is contour integration of third type, comma, where here a value must be greater than 0 using contour integration. Using contour integration, evaluate the integral. Okay. Now, by using contour integration, we can evaluate solution. Consider. Here is also we can use f of z as consider f of z as consider integral over c f of z as. Now here the function integrand function becomes cos ax divided by x square plus 1. We can consider this as, in terms of z, we can write it as we can consider this integration as we can evaluate integral minus infinity plus infinity cos ax divided by x square plus 1 x square plus 1 dx. This can be written as the numerator can be written as integral minus infinity plus infinity. The numerator cos ax can be written as real part of e power iax, real part of e power iax divided by x square plus 1 dx. Because e power I theta can be written as cos theta plus I sin theta. Cos theta plus I sin theta. Instead of cos ax, we can write it as e power iax. Okay. Now consider. Now we can consider the function integral over c f of z dz as, here we have to take the f of z as real part of integral over c e power I a z. Replace x by z, e power I a z divided by z square plus 1, or z square plus 1 dz. Consider this integration instead of in terms of z. Okay. Now, what is C here? Where C is a contour here, where C is the contour consists of upper of circle, like in the previous type, previous bottom, consist of upper of circle. Upper of circle, consider the circle as named as gamma of mod z equal to r. This is our upper of circle, and the real axis from from minus r to plus r. The axis from minus r to plus r. Now we can write the integration as integral c f of z, that is integral. Therefore, the integration can be written as integral minus r2 plus r f of x dx plus integral gamma f of z dz. The whole thing we can write it in terms of c f of z dz. Here the contour c as minus r to plus r from the real axis and the modulus of z equal to r. So gamma, circle gamma. So this is our contour. So we can split C as in terms of two. That is sum of two integrations. Now, by Cauchy-Residue theorem, we can write it as by Cauchy-Residue theorem. Cauchy-Residue theorem. By Cauchy-Residue theorem, we can write the right hand side it as 2 pi I into sum of residues of f of z at poles which lies inside C. Which lies inside. This is the formula for Cauchy residue theorem. So now we are going to find out the residues at poles which are lies inside C, and summing up with multiply with 2 pi n, we get the value of the integration. Now in the next slide we have to do to find what is f of z here. Here f of z equal to e power I a z divided by z square plus 1. Okay, the poles of f of z are the poles of f of z are given by the poles of f of z are given by equating denominator to 0. That means z square plus 1 equal to 0. This implies z square equal to minus 1, which implies z equal to plus or minus I. So we get two poles. Okay, z equal to I plus I is a simple pole. This pole, comma, lies inside C. Why? Because our contour is like this, the upper half of the circle. So I and minus I, I, 2I, 3I, 4I, 5I, 6I, all the positive values of i's are lies inside. Whereas in the negative values, minus I, minus 2I, minus 3I are outside the circle. That is outside the upper half circle. So therefore, z equal to minus I, z equal to minus I is a simple pole. Lie outside the circle. Outside our contour C. Okay. Now we are going to find out the residue. You can find out the residue at the pole lies inside C. Therefore, we have to find the residue. So residue of f of z at poles which lie inside. What is the pole lie inside? Z equal to I. At z equal to I. At z equal to I. We have to find the residue. Oh, already we discussed the residue formula. What's the formula for residue? Limit z tends to I, z minus I into f of z. That's a residue formula for a simple pole. So here we are to use limit z tends to I, z minus I into f of z. What is f of z here? E power I a z is our f of z divided by z square plus 1. Now instead of z square plus 1, we can write this as e power I a e power ia z divided by z minus I into z plus I. So in the factor form. Denominator, write it in the factors form. That is z minus I into z plus I. So cancelling z minus I, we will get e power, instead of z, we have to replace z by I, we get e power minus ia, e power I into a into I divided by I plus I 2I, which is equal to e power minus I into I square. This becomes minus a, e power minus a divided by 2I, which is the residue for the given function f of z and at poles lies inside C. So z equal to I. So the remaining pole z equal to minus I lie outside. We need to find out the residue for that pole. Okay. Now we're using equation number 1. From equation 1 becomes, therefore equation 1 becomes, equation 1 becomes integral minus r to plus r f of x dx plus integral gamma f of z dz equal to 2 pi I into sum of the residues. More than one residue means we can sum. We have only one residue. So sum of the residues e power minus a divided by 2I. Now the value of the integral in the right hand side is pi into e power minus a is our value of the integration. Pi into e power minus a. Now if r tends to infinity, the value r tends to infinity, then the integral over gamma f of z dz tends to 0 and z tends to x. Therefore, integral minus r to plus r becomes, that is integral minus r to plus r f of x dx plus integral gamma f of z dz, which is equal to pi into e power minus a becomes integral minus infinity, r tends to infinity, minus plus infinity, f of x, that is f of x here, instead of f of z we have to use x. So a real part of e power I a x divided by x square plus 1, x square plus 1, x square plus 1 dx plus the value of the integration is 0 here because we are letting r tends to infinity, pi into e power minus e. Now, what is the real part of integral e power iax? This becomes integral minus infinity to plus infinity cos ax divided by x square plus 1 dx is equal to pi into e power minus e. We know that integral minus constant to plus constant f of x even function. Integral function is even function. You can write it as 2 into integral 0 to the constant even function. It's a formula. So our aim is to find integral 0 to k even function can be written as 1 by 2 times of, 1 by 2 of integral minus constant to plus constant, even. The same sense we can use it here. That means here the function cos ax divided by x square plus 1 is an even function. So we can write this as 2 times, 1 by 2 times of, or we can write it as, it's an even function. We can write it as 2 into integral 0 to infinity cos ax divided by x square plus 1 dx is equal to pi into e power minus a. So our aim is to find the value of integration of 0 to infinity cos ax divided by x square plus 1 dx is equal to pi into e power minus a divided by 2, which is the value of the integration. So by using contour, we can evaluate the integration by using contour concept. Okay, thank you, one and all.